time to move on to our main event. And Craig, why don't you come on up? Craig's going to talk to us tonight about what is NoSQL and how does that work. So, all your turn. Testing? Testing? Okay, so I hope that works. Well, Craig is, maybe not. You ready to go?
Go ahead.
I was just going to ask if anybody had been looking into Java SE7 yet, or if you guys had any comments, but I think you're ready to go, so we'll hold that off for later. Thanks for coming tonight.
Okay, so my name is Craig Brown. We'll be talking about some NoSQL databases. We're going to try and give you kind of a high-level overview, more of an intro, cover some of the specifics about some of the products, compare kind of to the RDBMSs or SQL databases that we all know and love to use every day. So my goal is to kind of give a bit of an education here. I'll probably generate a lot more questions than I'm going to give you answers, but I think that's a good thing. I want you to be able to kind of think about how this relates to maybe some of the work you're doing, particularly the data model that you have, or the particular programming problems you can have. So a little bit about myself here. I work currently for a company called UJUG.com. It's a genealogy startup. A lot of you know me actually from Overstock. I left Overstock a couple months ago. Excellent place to work. A lot of great people there. Appreciate it a lot. So I have a blog that's up here that I have a lot more information on. You're welcome to go there and you know, check out some of the information that I have and the quick feed as well. So a little bit of the agenda here. We're going to kind of cover what is NoSQL and what's general, what's not. An overview of the landscape, some of the vocabulary, a little bit about the CAP theorem. Some of you will be familiar about that, but kind of governs how your data is kind of stored and replicated. A little bit of comparison between SQL and NoSQL data stores to try and take you from the kind of stuff that we know to the place that we don't know just yet. And then we're going to go through an overview of each type, a little bit of detail about what makes these different products unique and desirable, and we'll go through some questions. So NoSQL does not mean NoSQL. Actually, it has very little to do with SQL in general. NoSQL is supposed to mean not only SQL, so it's one of those kind of unfortunate acronyms that we have up here. The truth of the matter is they actually work really well together. Most companies do not, bring in a NoSQL data store and completely do away with all their SQL or RDBMSs. They're going to use their RDBMSs for what they're strong at. They're going to use a specific NoSQL data store to solve some particular problem that they're not able to solve or not solve as well with RDBMS. So this is a little bit of a breakdown. On your left-hand side here, I'm putting what I call row stores. This is a completely fair bunch here together, but this isn't the group that I'm necessarily concerned about talking about. But these are generally considered row stores because of the way they store the information on disk. Object relational is going to be slightly different there. On your right here, we have starting at the top, we have our column store database, which refers to how the data is kind of stored and accessed. And then next, we've got our document or key value stores. These are basically really big hashes. We're all used to dealing with hashes. The next one is a memory store. Memory stores and document stores are really similar in their data model, essentially the same, but their scalability model and their storage models tend to be quite a bit different. And the purpose, the reason why people are using these, this is one of the reasons why I've separated these. A lot of times you'll see them, these two kind of put together because of their data models being so similar. And the last one being graph or triple stores have to do with storing relationship kind of information. Bill knows Joe. Right? You can specify how strong that relationship is. And what is bidirectional? Maybe those that doesn't like them. So a little bit of history in the black here is SQL databases, and in the blue we've got the NoSQL data stores. As you can see, there's a lot of recent development, especially the last 5 to 10 years in the NoSQL space. A lot of these new data stores are coming up, and a lot of companies are developing these to solve very specific problems. And you see that when we talk a little bit about some of the individual categories. So a little bit about the vocabulary here, some of the things we're going to be talking about. So we have CAP theorem, which has to do with consistency, availability, consistency, availability, and partitioning. I usually have my screen here. My screen's blank at the moment. I apologize. I have to keep looking up here to make sure. So ACID commits. This is all the stuff that we really love with our RDBMSs. When we make any kind of a commit, we know there's guarantees on that. The polar opposite of that is called base transaction. So basically available, soft state, and eventually consistent. So those are probably going to be some new terms, but we'll talk about that a little bit more. It just has to do with how it stores and manipulates your data, especially in a distributed environment. RDF is an important one, the resource description framework. Has to do with the W3C committee on the semantic layer. So in other words, trying to bring meaning to all the information that we have out there. That has to do very much with your graph or triple store for that part. Sharding, it's just a little bit of a term for partitioning and distributing your data. And then the last one, web scale, is a term that generally means really big, right? Hundreds of millions or billions of rows of information, thousands of servers and clusters, the Googles, the Twitters, the Facebooks, they're really huge things. These companies are doing things that almost no other company in the world is doing. In a lot of cases, they have developed specific tools to be able to do this as well. So this is our CAP diagram. So the CAP theorem basically states that you can have consistency, availability, or partition tolerance, but not all three at the same time. So we've got a deal to make here. As developers and engineers, we're used to trading. It's like, yeah, I can get you that in a month, but I can't get you those features. One of those features is going to take 6 months, right? So consistency has to do with your clients and what view of the data that they get. If client A makes an update, what does client B see and how soon do they see that? Availability and partition tolerance are kind of two sides of the same coin, and they have to do with availability has to do with losing nodes, and partition tolerance has to do with basically your network and network tolerance. And so availability would look like, for example, if you lose a node, maybe your cluster is not available for reads, or your cluster is not available for writes, depending on what the situation is. So if you have a master-slave scenario where you're losing a master, which is a node, your data store may not be available for writes, but may be available for reads. Partition tolerance has to do with losing sections of your network. So if you have a switch that goes down, but your nodes are still available, what happens to the rest of the nodes? Can they communicate? When the communication is restored, does the network be able, or does your cluster be able to recover and do that? So normally what we live in is consistency and availability, and not necessarily partitioning. So that's a single node system. As soon as you add partitioning, as soon as you're dividing your data up over multiple nodes and multiple systems, then you've got some trade-offs to make. And a lot of times the trade-offs are made in consistency, but it depends on what the application is. So some of the parameters that go into tuning CAP, you have N, which is your number of copies that you make, your number of replicas of your data. R has to do with your read core, and write has to do with your write core, W1. So that's how many copies have to agree before you're going to consider that transaction successful, right? So for example, if you're keeping 3 copies of your data over your whole cluster, You can specify hard consistency, which would mean when I do a write, I want to make sure that all 3 copies agree before I consider that write successful. And that may be, very, very necessary depending on your situation. But it's going to be a little bit slower because you've got to have agreement between these 3 nodes, right? You could also say, well, this data is kind of not terribly important, I can regenerate it. I want to keep 3 copies, but I only want to make sure at least 1 copy is good. And then the cluster will take care of distributing the rest of those writes. But as soon as it gets 1 good write, it will acknowledge that and go on. It's kind of the same thing on reads. If you specify 3 copies and a quorum of 2 on read, you want to make sure if you read 3 copies, you've got at least 2 good copies before you're going to consider that read successful. So the 3 general types of consistency we have are hard consistency, which is what we generate with every day. Soft consistency is there's no guarantees, and that may work for some situations. And then eventual consistency is usually where a lot of the NoSQL data stores will live. I'm not going to go over this in too much detail, it'll be in the slide deck, but it basically gives you some ways of tuning or what it means. So hard consistency is basically when the number of the read quorum and the write quorum are the same as your number of copies. And then eventual consistency is when your number of writes is at least more than 1, but less than the number of copies that you decide to keep. And 3 tends to be the magic number here as far as the number of copies. If you're only keeping 2 copies, your data is not as secure. If you're keeping 4 or more copies, you're not necessarily gaining anything, but depending on the system, you can gain certain read performance advantages. So eventual consistency. So that means all replicas of your data will be consistent at some time. That may be in a few milliseconds, that may be in a few seconds. It depends on how many copies of your data you have and how large the cluster is, a lot of different things like that. And that's something to factor in. So for a lot of applications, eventual consistency works really well. So for example, if you're doing stock trades, you want hard consistency, right? If you place that trade, you want it now, you want to confirm. You don't want to find out later that it executed at $1 higher than you try to buy it at. You're not going to be real happy. On the other hand, your checking account is an eventual consistency system, right? You write that check, you give it to Walmart or Target, they're going to process it. It's going to get to your account, and it's going to be reconciled eventually, right? Could be a few days, whatever. So you have to kind of keep that into account. So there's various ways that these data stores work with consistency. So some of them will do what's called vector clocks, which is a way of determining what happened first. Did this read happen, or did this write happen, or did that write happen? It's basically tagging them with a big number. Some will actually use a real timestamp. Vector clocks are a little bit different than that. Another one is called read repair. So if you have 3 copies of your data and you have a read quorum of 2, and the database or the data store reads 3 copies, but one of those copies doesn't agree, it will go ahead and consider that a good read, and then it will go back and update that copy that was out of date. So it will update, it will repair itself on reads. Gossiping has to do with the cluster taking basically hashes of the information that they have and gossiping or sharing that with other nodes in the system to say, hey, this is what I understand the data to be. Is this what you understand it to be? And if they agree, great, you're good. If not, then they will decide what's the right information. They'll update themselves behind the scenes. The other way of doing it is essentially saying, okay, application, I got 3 copies of data. Here's your 3 copies. You tell me what's a good copy, and then I'll put it back for you. So it's kind of puffy about the idea of letting the application go ahead and deal with it. So we're going to run through some comparisons. On the left-hand side is our SQL column, and on the right-hand side is the NoSQL column.